Welcome to the TerrSet tutorial video series. Most of our previous tutorial videos have focused specifically on one modeling application within the TerrSet software. However, it is possible to create complex models and solve complicated problems by combining multiple modeling applications available in TerrSet. This tutorial video will demonstrate how to use multiple modeling applications, including the Land Change Modeler, Climate Change Adaptation Modeler, and Ecosystem Services Modeler to complete an analysis of water yield in Massachusetts for the year 2100. Water yield is a measure of the average annual runoff within a study region and can provide insight on diverse topics such as erosion and drinking water supply. A water yield model is available within the Ecosystem Services Modeler in TerrSet. 8 inputs and 1 additional parameter are required for this model. Among the necessary inputs are a land cover image and a precipitation image for the modeled year, in this case 2100. We can create the land cover prediction using the Land Change Modeler and the precipitation prediction using the Climate Change Adaptation Modeler. The other inputs can also be created or derived using tools available in TerrSet, but I'll focus on these 2 inputs for this video. Let's start with the Land Change Modeler. The LCM application in TerrSet can be used to analyze land change over time and to predict future land change. In this demonstration, I want to use the LCM to predict land cover in Massachusetts for the year 2100. I first need an earlier and a later land cover image from which to extract the trends in land cover change that will then be extrapolated to our target year of 2100. The 2 land cover images are from 1996 and 2006. In order to focus on only the largest transitions, I'll specify a threshold of 12,000 pixels. It seems that the largest transitions in Massachusetts between 1996 and 2006 have been conversion of deciduous forest to other land cover types, a process that is likely to affect water yield. I'll focus in specifically on the transitions from deciduous forest to developed land and combine these transitions into a single submodel. Next, I'll specify some constraints on the model so that protected areas won't change regardless of their similarity to areas that changed between 1996 and 2006. Now, I can insert a layer group of driver variables that are causing the conversion from deciduous forest to developed land and specify the role for each of them. All of the variables included in this model are static, except the distance to developed land variable, which I want to dynamically update at each time step in my model. I'll specify the role as dynamic, the basis layer type as land cover, and select the developed medium intensity as the dynamic land cover class. Then leave distance as the operation type. I now need to create the transition potential images for my model using the MLP neural network. These are the transition potential images for the 3 transitions I just modeled. Finally, I can specify the prediction year to be 2100, select to use 4 time steps in the modeling process, and create my final image of land cover in Massachusetts in 2100. This was a very quick run-through of the Land Change Modeler, so check out the LCM tutorial videos, the TerrSet tutorial, or the help system for more information on the Land Change Modeler application. The next input I need for the water yield model is a prediction of precipitation in 2100. I can use the Climate Change Adaptation Modeler to create this prediction. CCAM can also be used to generate climate change scenarios and analyze the impacts of different climate scenarios on sea level rise, species distributions, and crop habitat suitability. We'll use the data and tools in the MAGIC and SceneGen panels developed by the National Center for Atmospheric Research and incorporated into CCAM to calculate and predict precipitation change by the year 2100. First, I need to run a global warming model. I'll use the default emission scenario and keep all other parameters at their defaults as well. Then, I need to create a prediction of precipitation for 2100 using the Generate Climate Scenarios panel. I'll make sure I'm creating an annual model of precipitation for the year 2100 and leave all other parameters at their defaults. The output is a global estimation of the absolute change in precipitation between my reference year of 1990 and my prediction year of 2100. I need to make a number of changes to this prediction before I can use it in the water yield model. I've used basic image processing and GIS tools, including Window, Reclass, Project, and Overlay, to narrow my global precipitation prediction down to just Massachusetts. However, I have two other changes that I still need to make. First, the precipitation prediction created by CCAM is measured in millimeters per day, and I need to know how much precipitation has changed over a whole year. I'll use the scalar module to quickly multiply the precipitation change in millimeters per day by 365 days in a year to create an image depicting precipitation change over an entire year. The next issue is that the precipitation prediction is a prediction of change from a baseline, not an image depicting total annual precipitation in the year 2100. The baseline I used when making the prediction was the year 1990, so in order to create a layer of precipitation in 2100, I need a layer of total annual precipitation in 1990, to which I can then add the predicted change image. I've downloaded and processed data from the PRISM Climate Group to create this image of total annual precipitation in Massachusetts for the year 1990. I can now add the change layer to this baseline layer using the Overlay module to create a layer of total annual precipitation in Massachusetts for 2100. The 1990 and 2100 precipitation images look similar, but if you check the individual pixel values, you can see that, in most locations, total annual precipitation is higher in 2100 than in 1990. Again, this was a quick run-through of modeling climate change impacts using CCAM, so check out the TerrSet tutorial or the help system for more information on the CCAM application. Now I'm ready to open the Ecosystem Services Modeler and set up my water yield model. The water yield model, once provided with the necessary inputs, will create a prediction of the average annual runoff or water yield for your study area. Water yield can be used to look at many topics of potential interest to policymakers, including flood risk, hydroelectric dam potential, drinking water availability, drought risk, and erosion. To run the water yield model, I simply need to specify the inputs. Mass watersheds and mass subwatersheds are layers depicting the watershed delineations in Massachusetts. The biophysical table is a CSV file that contains information about water movement over each type of land cover in our predicted land cover image. The data for this input may be complex to collect, but the necessary file can be created easily in Excel or by using the text editor in TerrSet. We just created the land cover and precipitation predictions. There are several other inputs for the water yield module, including an evapotranspiration image, restricting layer depth image, and plant available water content image, as well as an additional seasonality factor parameter, which you can read up on in the TerrSet tutorial or the help system files. Finally, I can give the output file a name and hit Run. There are three outputs, each showing the average annual runoff or water yield at a different scale in the study area. The smallest scale analysis is the pixel level, then subwatersheds, then watershed level runoff. These outputs can be used for your own analysis or may be used as inputs into other TerrSet models, including the hydropower and water purification models within the Ecosystem Services Modeler. For more information on the modeling applications and modules used in this tutorial video, check out the TerrSet tutorial, which can be accessed by going to Help and selecting TerrSet Tutorial. Tutorial exercise 7-1 will walk you through the tutorial demonstrated in this video. You can also learn more about any TerrSet module by accessing the Help System files, either by going to Help, Contents, or by clicking the Help or question mark button on any TerrSet dialog box or modeling panel.